Hi, I'm Nicholas Meegan from SRI International, and I'll be presenting our work GeoSURGE, Geolocalization using Semantic Fusion with the Hierarchy of Geographic Embeddings. The problem we focus on is worldwide visual geolocalization. The input is a single image taken anywhere on Earth, and the goal is to predict the GPS coordinates using only the image itself, so there is no metadata or external information giving away the location. This is a hard problem because the visual world is extremely diverse. Two places that are geographically close can look completely different, while two places on opposite sides of the planet can look very similar. On top of that, images often contain dynamic objects like people, cars, or temporary scene elements that are not actually useful for localization. Most prior works fall into two broad categories. Retrieval-based methods compare the query image against a large database of geotagged reference images. Classification-based methods divide the world into geographic cells and predict which cell contains the query image. Retrieval can be accurate, but it depends on a large reference database. Classification is efficient, but it treats geographic regions as discrete labels. And GeoSURGE tries to bridge these two ideas. We still divide the world into geocells, but we do not treat each geocell as just a class ID. Instead, each geocell has a learned embedding, so the model learns a representation of geographic space, and the task becomes matching an image embedding with the right geographic embedding. The overall pipeline is shown in Figure 1. We start with the RGB image, and we also generate a semantic segmentation map using OneFormer. The RGB image goes through a clip vision transformer to produce appearance features, and the segmentation map gives us a more structural view of the scene. The reason why we use semantics is that not every pixel should matter equally for geolocation. Some regions are stable and location informative. Other regions, like people or vehicles, may be visually prominent but unreliable. This map gives the model a way to reason about that structure. The next part is our semantic fusion module, shown in Figure 2. Rather than just concatenating RGB and semantic features, we use latent cross-attention. In this module, the semantic tokens are the queries, and the RGB appearance tokens are the keys and values. The semantic structure guides how the model aggregates visual appearance information, and the output is a fused visual representation of the image, which we use for matching against geography. On the geography side, GeoSURGE learns a hierarchy of geographic embeddings. We use S2 cells to partition the Earth at multiple spatial resolutions. Coarse cells capture broad geographic context, while finer cells provide more precise localization. Each geocell at each level learns its own embedding. During training, we know the GPS location for each image. That coordinate tells us which geocells contain the image at each level of the hierarchy. We then train the image representation and the corresponding geographic embeddings with a contrastive objective. The model is encouraged to give high similarity to the correct image geography pair and lower similarity to the incorrect pairs in the patch. At inference time, given a new image, GeoSURGE computes the fused visual embedding and compares it to the learned geographic embeddings. The final prediction is made hierarchically by combining evidence from the fine geocells and parent cells. So the prediction is not coming from one flat classifier, but the agreement across multiple geographic scales. For evaluation, we use 5 standard benchmarks in the literature. We report accuracy at 5 distance thresholds which roughly correspond to street, city, region, country, and continent level localization. Across these benchmarks, GeoSURGE achieves state-of-the-art performance on 22 out of 25 of the metrics. If we exclude methods that use large vision language models, GeoSURGE is the best on all 25 metrics. A key comparison is GeoClip, since it also uses clip-style alignment. GeoClip represents locations using GPS coordinate embeddings, while GeoSURGE uses learned embeddings over all hierarchical geocells. The improvement suggests that the geographic representation is doing a lot of the work. The qualitative results show the same trend. In successful examples, the model uses semantic and appearance cues together to focus on stable scene structure. One example shown here is the Eiffel Tower versus the Las Vegas replica, where surrounding contexts like water and nearby buildings help disambiguate the location. The ablations help separate the contributions. Increasing the hierarchy depth generally improves performance, especially at finer thresholds. Semantic fusion improves the overall balance across benchmarks, particularly for fine-grained geolocalization. And the geographic representation ablations show that the hierarchy and learned geocell embeddings are complementary. The best performance comes from using both together. The main takeaway is that the explicit geographic modeling is still very valuable for worldwide visual geolocation. Instead of representing a location only as a low-dimensional GPS coordinate, GeoSURGE learns a structured, multi-scale embedding space for geography and aligns the images to that space. Looking forward, an interesting direction is combining structured geographic representations like this with LVLMs or agentic systems. Rather than asking a large model for a single answer in one forward pass, future systems could combine learned geocell embeddings, retrieval, map structure, and reasoning. Thank you for watching, and I hope you'll come by the poster to discuss GeoSURGE.